Let's go ahead and calculate a more complex shape. So give yourself some room to the sides and the top. Start with a 12 by 12 square with some cutouts. So let's count it out quick. 2, 4, 6, 8, 10, 12. Okay, and then on the right, at the bottom, it'll also be a 12 length. But then up here at the top, let's do half that. Let's cut out a part of it. So we'll go 6. So what is that about right here? This is 6. 2, 4, 6, yes. We'll do the same thing down here. So 2, 4, 6. Drag it down. Just drawing a quick, complex shape, and then connect these with a corner. And let's say the shape is at a scale of 2 to 1. In other words, if this thing is 12 squares long, then we're going to say it is 6 inches. It's twice as big. And then therefore this smaller area, which is only 6 squares long, that's just 3 inches in length. And the same is true down here. The 6 square length is just 3 inches. And then therefore we could say this entire thing is 6 inches tall. And so as you can see, we have multiple shapes combining. Therefore their centroid, or their average mass, will also combine. So what we're going to do is we're going to take the average mass of each individual shape. I count 3. Let's go ahead and separate these real quick. I count 3 shapes. We got a rectangle here, and then we got a triangle and a square here. And each one has its own average mass or centroid, and they're going to combine to make a total centroid. Let's go ahead and let's think about it for a second. We have more weight here on the bottom left than we do at the top right, so wouldn't the centroid be pulled down onto the left a little bit? Well, let's see. So let's call this one, this rectangle shape 1, I don't know. Let's call this triangle shape 2, and then let's call this square down here shape 3. And let's start by calculating the average, or I'm sorry, the area, not average, the area of each individual shape. So for example, area 1, well, it's a 3 by 6 rectangle. 3 times 6 is 18 inches squared. And the area for shape 2, this triangle, it's a base of 3 and a height of 3. Well, the formula for the area of a triangle is base times height divided by 2. 3 times 3 is 9 divided by 2. So area for shape 2 is 4.5 inches squared. And shape 3 is the easiest one of all. It's just a 3 by 3 square, so that area is just, of course, so area for shape 3 is just 9. And the reason why that's so important is because this triangle has a smaller area than the other 2 shapes. So it's going to affect the average mass of the entire shape at a lower amount. Its area is smaller, so its average, or its addition to it, is a much smaller value. The last thing we need is to label our reference point. I'm going to start with the bottom left, just to keep a consistent place to measure from. Let's go ahead and find out where our centroids are. So this first one is clearly going to be halfway across our rectangle in the x direction. This is going to be, let me pick a fatter color here. This is going to be our x1 distance to our centroid, whereas this will be our y distance to our centroid for shape 1, or I'm just going to call it y bar 1. Okay, so what are these numbers? So x1, or the distance from our reference point to our centroid here for our first shape. Let me go ahead and mark that as our first centroid here, this location where these two meet. That is just, well, it's 3 squares, which is 1.5 inches, because remember this is a scale of 2 to 1. And then our y distance is, of course, just 3 inches from our reference point. What about our second centroid? Or yeah, what about for our second shape? Okay, that's a triangle, and we learned that it's the base divided by 3 and the height divided by 3 would be the place for the centroid of your rectangle. Okay, so it's just 1 inch in and 1 inch in. But that's not what we care about. We care about the distance from our reference point. So it would be here and here. This is our centroid, which is 1 away from the bottom corner of our triangle, but we want to know what the distance is in the x direction from our reference point. So this is x2, and this will be y2. And x2, or our distance from our reference point to our second centroid in the x direction, is what? It's 2, 4, 6, 8 squares, so that's 4 inches. And y2 would only be 4 inches as well in the y direction. Then the third shape, the centroid, is incredibly easy. It's just right in the center of our square, right? And so that's just 1.5 from one edge of the square, 1.5 from the other. We don't care about all that. We care about the distance from our reference point. So that's here. That is our x bar 3. And then, of course, we follow along, and this is our y distance for our third shape to our centroid and our reference point. And so our x3 is just, what, 2, 4, 6, 8, 9, so 4.5 inches from our reference point. That makes sense because it's, you know, half more. This is a 3 by 3 square, and that means it's 1.5, and then it's 4 away. Okay. Or the square is 3 away from our reference point, and that just makes sense. Okay. Y in the third. What about our y3? Now that we're off our little ramble on our x. What is it? It's 1.5 inches, or 3 squares. 1.5 inches. You remember our formulas for our x and y are both the same. For the x total centroid, it's the sum of all x individuals multiplied by the area individuals divided by the sum of all area individuals. And our y total is the exact same equation, just with a y instead of an x. So the sum of all y individuals, and this should have a bar over it. And for that matter, the other one should have had a bar over it. Let's go ahead and go back, fix my OCD. Y individuals times the area individuals divided by, of course, this is the sum of all area individuals again. And so let's just plug in our numbers real quick. What do we got? We got our x first. Let's say the x total equals, and okay, I'll put a big line here to write. We'll say x times a for the first shape, so that's 1.5 inches for the first shape multiplied by 18, its area, plus we'll say the area for our x, or the x distance, sorry, multiplied by the area, 4 times its area, which is 4.5. So the x individual at 2 multiplied by the area individual at 2, and then we'll add that to, of course, what we got here. We got 4.5 times 9. Okay, so our x distance was 4.5 this time, and our distance was 9. And meanwhile, on bottom, we'll just add up our individual areas. So 18 plus 4.5, draw that right, plus 9. Okay, cool. So this is pretty easy to simplify. We could set this all equal to 1.5 times 18 would be, what, 27? 4 times 4.5 would be 18. Let's actually color code this, so this should be 18 in green. And then 4.5 times 9, what is that? Well, 9 times 4 is 36, times a half is 4.5, so it would be 40.5 on top. And then on bottom, what will we put? 18 plus 9 is 27, plus 4.5 would be 31.5, if I'm not mistaken. So let's pull out our handy-dandy calculator. What is 27 plus 18 plus 40.5? We get 85.5, and then we can divide that by 31.5. And what do we get? We get a total distance in our x direction of 2.7. So equals 2.7. Which would be about, I don't know, about right here. Would be our x total. And y is essentially going to be the exact same thing. What do we got? We got y total equals, what are our numbers here? Let's go ahead and draw ourselves a little bar out. We've got our x distance in the y direction is 3 times its area, which is 18, and then we'll add that to the 4 times 4.5 again, because it was the exact same. So 4 times 4.5, and then the y distance multiplied by the area for shape 3 was 1.5, so plus 1.5 times 9. And of course, the numbers on bottom are the exact same. We got 18, we got 4.5, and we've got 9. And actually, we don't really need to simplify. We can just plug this in our calculator exactly as it's written. So what would I say? I'm just going to type this with my keyboard. It's a little bit faster. 3 times 18 plus 4 times 4.5 plus, oh, actually, let's go back. make that a parentheses first, plus 4.5 times 9. Then on bottom, oh wait, that's 1.5, I'm sorry. Let's go back up, fix that. I'm copying down the wrong formula. I want this formula right here. It's 4 times 4.5 and 3 times 18, yes. So we go down, and we can type it in on bottom, the same thing, 18 plus 4.5, let's go back, 0.5 times, or plus 9. Now let's see what we get. And we get the exact same answer, because of course we do, because this thing is symmetrical. So let's go ahead and write that equals, let's do this in the right color here, equals 2.7. Because, well, duh, so let's go up 2, 4, 6, a little bit less here. And so these dots are going to meet here, and let's do purple, here, and that'll give us our total centroid, which would be along our line of symmetry. And you might be thinking to yourself, well, what line of symmetry, Mr. Anderson? It's cut off on the top and the side. But if you look at this diagonal line of symmetry, that definitely exists. And of course, the centroid's going to be along it. And so we added up all of our different shapes and their average masses and their distances from our reference point, and that gave us the total centroid for our two distances here. 2.7 in the y direction, 2.7 in the x direction, and we call this the addition method for solving for centroids. So addition method. So kind of a long process, but hopefully not a hard process, just plugging in numbers and looking at shapes.